Good afternoon, or good evening, whichever suits you depending on the time you are watching this video. Talking to you is Kalulu Ronald, and I'm a teacher of A-level chemistry, and today I'll be taking you through one question, and that one you already displayed on the screen. You can read through that question, analyze it, or write it somewhere. Then we go through it as required by the abridged curriculum for A-level. So this question here is coming from a branch of chemistry called physical chemistry, and it is saying Kawanda Industrial Chemicals Limited is one of Kenya's leading manufacturers of sulfuric acid used in fertilizer production, battery manufacture, petroleum refining. Here and is missing, and petroleum refining. During internal auditing, the production manager observed that the conversion of sulfur dioxide into sulfur trioxide had fallen below the expected value, which increased production costs and caused more sulfur dioxide to escape. They have already created a problem here. They are saying that this conversion here, the conversion of sulfur dioxide to sulfur trioxide has fallen. That is the problem in our scenario. Below the expected value, which has increased the production costs and causing more sulfur dioxide to escape into the environment. So sulfur dioxide is escaping into the environment because in our production process, we use sulfur trioxide to form sulfuric acid. So the sulfur dioxide which is not converted to sulfur trioxide may find no use, and thus it will be left to, or it will escape into the environment. Otherwise, if it was being converted into sulfur trioxide, then it would have been used in the manufacture of sulfuric acid or fertilizers, as they talked about it above here. The neighboring community raise alarms. Here they are telling you that the escape of sulfur dioxide or even sulfur trioxide is making the neighboring communities to raise alarm to the environmental officer. Whenever you see such a statement, it is evoking you to discuss at least a mitigation and a danger and a mitigation. So they have raised the problem here, and they have sought, or they have added on that you should discuss a danger and a mitigation. This information comes indirectly. They will not tell you directly. The technical team collected the following information from one of the converters, and the reaction we are talking about is this one, and they are telling us that this reaction is reversible and exothermic. That is the reaction we are talking about. It is reversible and exothermic. Then they said a 10.0 decimeter tubed equilibrium vessel was charged with 6.0 mole and 4.0 mole of sulfur dioxide. So they got one of the converters or one of the vessel where the reaction is taking place, and they added there 6.0 mole of sulfur dioxide and 4.0 mole of oxygen. And we know when the reaction is reversible, it never goes to completion, instead attains an equilibrium constant. So they are saying that by the time the reaction attained equilibrium, it contained 3.2 moles of sulfur trioxide. It contained 3.4 moles of sulfur trioxide. This is what I'm talking about. We got 6.0 mole of sulfur dioxide and 4.0 mole of oxygen, and at equilibrium we had 3.2 moles of sulfur trioxide. The engineers also investigated the flow of the reaction based on the operating conditions, and here the operating condition is Remember, they began by creating a problem that less of sulfur dioxide is being converted to sulfur trioxide. So in this, they are trying to adjust on the operating condition. Their aim is to adjust on the production of sulfur trioxide. So one thing they are doing, they are raising temperature. Another thing, they are increasing pressure. They are trying to add a vanadium pentoxide catalyst or bringing in excess oxygen. They don't know how to optimize sulfur trioxide. All of this, they are doing it by guesswork. The audit team has failed to make a comprehensive report and you have been consulted for help. Then the task is analyze the equilibrium data and assess the operating conditions and applications of the reaction. So we are going to answer this question and we are beginning with part A, analyzing the equilibrium data. When you are told to analyze the equilibrium data, but when you have been given volume, you can see that here we have been given volume, this one. When you have been given volume, then analyzing the equilibrium data, they are asking you to find the equilibrium constant in terms of Kc. Because you have moles and you have volume, and we know that the concentration is moles per decimeter cube. That is moles divided by volume. So it gives us concentration, and the equilibrium constant in terms of concentration is Kc. But if you are not given volume and you are given moles, and instead of volume you have been given total pressure of the system or the gaseous mixture. For example, they say 6.0 mole and 4.0 mole of sulfur dioxide and oxygen were respectively charged into the vessel, and at equilibrium it contained 3.2 mole of sulfur trioxide. Full stop. The total pressure or the total pressure of the system was 1 atmosphere. Instead of giving you volume, they are giving you now pressure. For that case, you find the equilibrium constant in terms of pressure, and that is Kp. So I'm saying we can have Kp and we can also have Kc. So what you are given determines how you analyze the data. So for this case, we have volume and we have moles, so we are going to look for Kc. So this question, hope you've got it. I'm going now to go to the page where I will hide this question, but calculate. So let's come here and determine our Kc. So in addition to this information I've got it from the question, and in addition to this information, there is volume of the vessel. These are gases and they occupy the volume of the vessel. It is 10 decimeters cubed. If volume is given in any other units other than decimeter cubed, then for that case you have to convert that volume to cubic decimeters. Alright. So what I will do, I'll come up with an ice table. Ice table, I mean initial concentration that reacted or formed, then equilibrium concentration. So this is my table here, and in this table I have item. Then here I'm going to get this equation, which is attaining equilibrium, and I copy it into the table. So here I have sulfur dioxide, but 2 moles. Then I have oxygen, and I have sulfur trioxide. I'm just copying that equation into my table, gas and gas. Then after that, I have initial moles, and initial moles for sulfur dioxide have been given it here. You can check here. Sulfur dioxide initial moles are 6.0 and oxygen they are 4.0. So here I have 6.0 and here I have 4.0. But remember, in this process, oxygen react with sulfur dioxide, form sulfur trioxide. So by the time I was beginning, there was no sulfur trioxide formed because the reaction was just starting. Then after that, some sulfur dioxide and oxygen will react, and therefore here I'm going to have moles of oxygen and the sulfur dioxide reacted. Sorry, let me write it in a more better way. I'll just say moles reacted stroke formed. Moles reacted stroke formed. So after that, I write there moles reacted stroke formed. For reactants, they react. For products, they form. Then after that, I'll go to moles at equilibrium. Then after moles at equilibrium, in my case, what I want is concentration at equilibrium. So I will come here down and put concentration at equilibrium. Concentration at equilibrium. Now I fill in. Besides the information I have already filled in the table, the other information I've been given is all about moles of sulfur trioxide, which are there at equilibrium. So here, moles of sulfur trioxide at equilibrium, I have 3.2. But if sulfur trioxide present at equilibrium with 3.2, all those moles of sulfur trioxide present at equilibrium were just formed. So moles of sulfur trioxide formed are also 3.2. Then you look at the mole ratio. Mole ratio of oxygen to sulfur trioxide is 1 to 2. So if moles of sulfur trioxide are 3.2, then those of oxygen will be 1 out of 2 times 3.2. This one gives me I'm getting my calculator here, 1 out of 2 times 3.2, it gives me 1.6. So here I get 1.6. Then this is a mole ratio of 2 to 2. So moles which are here are the same as moles which are here. So here I have 3.2. Now, if I had 6.0 moles and 3.2 reacted, here I remain with 6 minus 3.2 which reacted. What remains is 2.8. I had 4 moles of oxygen and 1.6 reacted, so I remain with 2.4. This is 4 minus 1.6, I remain with 2.4. So these are now the moles at equilibrium, but remember we need concentration at equilibrium. But we know that concentration is the same as moles out of volume. Concentration is moles out of volume. This is what I'm saying. Concentration is mole per decimeter cubed. So it is moles out of volume. So I'll get these moles divided by the volume and I get the concentration which is here. So for this case it will be, let me pick another ink, it will be 2.8 divided by 10. Then here it will be 2.4 divided by 10 because volume was 10 decimeter cubed. 3.2 divided by 10. Then after getting concentration at equilibrium, you can now calculate your Kc. So I'll write the expression for equilibrium constant Kc of the reaction, but I write it deriving it from this equation which is here. Kc is a concentration of the product raised to this stoichiometric value in a balanced equation divided by the product of concentration of reactants also raised their stoichiometric values in a balanced equation. So by following that, I'll say Kc is equal to concentration of sulfur trioxide but squared divided by concentration of sulfur dioxide squared concentration of oxygen, but for it, when you look at the equation, it has no stoichiometric value. It has it, but it is a silent one, so powering one is the same as leaving it the way it is. But you also have to move along with the units. The concentration of sulfur trioxide is in mole per decimeter cubed, but this one is squared divided by concentration of sulfur dioxide and concentration of oxygen are also in mole per decimeter cubed, but this is squared and this is power 1, so when you add, the denominator goes to power 3. So I now put in my Kc will equal to sulfur trioxide, its concentration is 3.2 divided by 10. That is the same as 0.32, but what? Squared divided by concentration of sulfur dioxide 0.28, but what? Squared. Then concentration of oxygen is 0.24. When you come to the side of units, this squared can cancel. I remain with 1 out of mole per decimeter cubed. You have always to move along with the units because wrong units makes your answer to be wrong. Even if the answer is right in terms of the digit, if units are wrong, then the answer becomes wrong. So when you punch this one in the calculator, you get 5.44. You can ignore other values and write this. So the units are now per mole decimeter watt, decimeter cube. So this one becomes our value of Kc. But after getting that value of Kc, remember we also have to always interpret our data, and whenever you get Kc equal to that, it is required of you to interpret the value of Kc in terms of the position of the equilibrium. And whenever you get Kc which is less than 1, it means something. If Kc is greater than 1, it also has something it means. And if Kc is equal to 1, these one have implications. If Kc is less than 1, then that one means the equilibrium is shifted to the left. It means that the equilibrium is shifted to the left. And if you get Kc which is greater than 1, then it means that equilibrium is shifted to the right. Then if you get Kc which is equal to 1, it means that the equilibrium is centrally positioned. It is not to the right and it is not to the left. It is central to the reaction. So if equilibrium, remember, the case we are talking about is all about the product divided by reactants. So when do I get a value which is less than 1? I get a value which is less than 1 when the numerator is smaller than the denominator. Take an example. 2 out of 5 gives me a value which is 0.2 divided by 5. gives me a value which is 0.4. It is less than 1. So a Kc value which is less than 1 means that the numerator concentration is less than the reactant's concentration, meaning reactants are dominating and the reactants in our equation are always on the left. That is why we are saying the equilibrium constant is shifted to the left. Then the opposite is true for Kc greater than 1. So now, when you look at our answer, Kc is equal to 5.44, a value which is greater than 1. Since it is a value greater than 1, then interpretation we shall say, since our Kc is greater than 1, this is our interpretation here. Since our Kc is greater than 1, since our Kc is greater than 1, the equilibrium is shifted to the right, and this implying at equilibrium concentration of sulfur trioxide is more than concentration of product C. At equilibrium, the concentration of the product is more than the concentration of the reactants. And you can look at our values above. The concentration of sulfur trioxide was 0.32, concentration of oxygen was 0.28, and concentration of sulfur dioxide was 0.24. So the product is dominating in terms of concentration. Alright, so that is our interpretation. Now, after interpreting, you go back to the question and look for other marking areas. You don't end there. So when I come here back to the question, it tells me that I have finished analyzing the equilibrium data, but it has part B. Part B saying assess the operating condition is and application is of the reaction. So the operating condition is this one. They are just asking me by adjusting the operating condition is like this. Am I increasing the yield of sulfur dioxide or not? So the first operating condition is increasing the temperature from 450 to 600 degrees Celsius. But you know very well that when you look at this reaction, there is an dH equal to negative, meaning the process is exothermic. And when the process is exothermic, what does it mean? If the process is exothermic, this is how the energy profile diagram will look like. Here I have sulfur dioxide and oxygen, then here I have sulfur trioxide. Then this is my dH. We know that dH, this is potential energy and this is time of the reaction. Then this one is the activation energy. So we know that dH is given by enthalpy of products minus enthalpy of reactants, which is sulfur dioxide and oxygen. But for this case, the products are at a lower enthalpy than the reactant. That makes the dH to be negative, meaning the reaction is giving out what? Is giving out heat. And if a reaction is giving out heat, then if you want to increase its reaction, you don't also increase temperature. It is giving out heat. In order for you to increase the reaction, then you have to lower down the temperature. But as you are lowering down the temperature, you have to remember that this reaction requires a minimum amount of energy, which we are calling activation energy. So here I will say when temperature was increased, the equilibrium was shifted from right to left, decreasing the yield of sulfur trioxide. Because the reaction leading formation of sulfur trioxide is exothermic. That will be the explanation for this temperature. For temperature, when temperature, let me first clean here. When temperature was increased. Oh, I'm receiving some challenge with my pen, but that is what will happen for temperature. The equilibrium will shift from right to left because the formation of sulfur oxide is exothermic. So you explain that factor. Then you come and pick another factor. Another factor is talking about pressure of the system being increased. But when we look at our reaction, these are 3 moles on the left and these are 2 moles on the right. So we are moving from bigger moles to fewer moles. So increasing pressure will increase the rate of reaction, leading to formation of more sulfur dioxide and shifting the equilibrium to the right. So for temperature, we are saying when you increase it, sulfur trioxide production decreases. And for pressure, when you increase it, sulfur trioxide production increases. You have to explain and always talk about the position of the equilibrium. And another one is addition of a catalyst. And we know that when you add a catalyst, it shortens the time we take to obtain the equilibrium, but it does not affect the equilibrium position. So when we add vanadium pentoxide catalyst, we say equilibrium is attained faster. But not affected. Equilibrium is attained faster but not affected. If equilibrium is 5.44, like we are seeing here, our case is 5.44, it will remain 5.44, but it will be attained in a shorter period of time. Another operating condition they are talking about is excess oxygen supplied. When you supply excess oxygen to the system, you have to remember what Hitler says. Hitler says that addition of an external concentrate to a reaction at equilibrium, it makes the equilibrium position to shift in a way to overcome the external concentrate added. So if I add oxygen, I'm increasing reactants, and some reactant have to be converted to product. So if I add their excess oxygen, meaning I'm increasing oxygen, sulfur trioxide production will also increase and equilibrium will go to the right. So this is also right, and this one is left. This is what I'm trying to talk about. This one is my A. This diagram is A and this diagram is B. In A, if I have equal weights here, this one can attain equilibrium. It can attain equilibrium in A. If the weight here is equal to the weight here and the distance for them from the pivot is the same, then this one will be in equilibrium. But if I come and I add more weight here, but I maintain the weight which is this side, this one, the equilibrium will be shifted, so that if I want to get back at the equilibrium, I have to move some weight and take it this side, so that I get back the equilibrium. So that is what is happening, and that is what Leschner says. Addition of excess oxygen increases the reactants, and that one destroys the equilibrium. So some oxygen has to be converted to the product in order to get back at the new equilibrium. So you explain those factors. Then remember our question talked about application, assess the operating condition and application of the reaction. So how is the reaction being applied in daily life? So here I'm going to talk about application. So here I'm going to talk about application. And when you talk about application, you move away from chemistry in books and you go to industries, and real application is at home. So that reaction, we apply it during the manufacture of sulfuric acid, or manufacture of fertilizers. You choose one and explain how. So what happens is that the sulfur trioxide obtained is dissolved in sulfuric acid to get oleum. Then you can write in equation the fact that by now we believe you are mature enough to work with equations. So you make sure you add an equation there to support your answer. It is reacted to form oleum, S2O7. Then after that, oleum is diluted with water to form sulfuric acid. Then you write an equation to support that statement also. We are saying if you have oleum and you add there water, then you'll be able to form sulfuric acid. This is a liquid, even this one is a liquid. Oleum is a liquid because it is too concentrated. That is why I put a liquid, but otherwise it would have been an aqueous solution. But because of the very high concentration of sulfuric acid there, we make it to be a liquid. Even this one, if I add less water, the sulfuric acid I form will be highly concentrated, and I will have to dilute it with more water to put it to the desired concentration. Okay. So there I have discussed an application, but if someone chose fertilizers, then that person would continue and add that sulfuric acid formed is reacted with ammonia. To form ammonium sulfate, and ammonium sulfate is agriculturally used as a fertilizer. Ammonium sulfate is agriculturally used as a fertilizer, like I told you. So for that case, we are using the reaction to form fertilizers. So you have to support it with an equation. This is ammonia, which is a gas, and I'm going to react it with the sulfuric acid I have formed, and I'll end up forming ammonium sulfate. Ammonium sulfate. This one will appear as an aqueous solution, but you can crystallize. Chemistry has been advanced in many ways, to the extent that we can manipulate it in many ways that we want. So I will put a 2 here to balance the equation. So that is an application, but I have not yet fully answered the question, because the question, remember, when I was taking you through here, it talked about the people who are alarming to the environment officer due to the ejection or escape of sulfur dioxide and sulfur trioxide into the atmosphere. So that one evokes you to talk about a danger and a mitigation. So I'll come here and talk about a danger. If sulfur dioxide or sulfur trioxide is escaping into the environment, which dangers will it cause? So here I'll talk about a danger, and every danger I talk about goes with a mitigation. So danger and mitigation. Danger and mitigation. So there are many dangers, but now I'll talk about one or two. The danger I'm talking about now is that addition of sulfur trioxide and sulfur dioxide into the environment can cause acidic rains. My pen is freezing, so bear with the speed. Can cause acidic rains. And how does this can be mitigated by? You complete. My pen has issues now. It's freezing. This can be mitigated by, actually the danger is not complete, because what's wrong with acidic rain is you have to explain the danger. Addition of sulfur trioxide and sulfur dioxide into the environment can cause acidic rains, which change soil pH, affecting plant growth. That is the danger. This can be mitigated by either you can talk about addition of catalytic converters in industry chimneys, such that the escaping sulfur dioxide can be converted into harmless products, or you can talk about application of organic or alkaline fertilizers, which can help to raise the soil pH. That is the first danger. Another danger is that inhalation of sulfur dioxide and sulfur trioxide can result respiratory disorders. Can result to respiratory disorders. And if we have respiratory disorders, how can we mitigate that? People who are prone to exposure of sulfur dioxide and sulfur trioxide should consider working while wearing gas masks in order to reduce the inhalation of those toxic fumes. So after answering all that, then you say you have finished answering. And when it comes to scoring, this is how they will score your work. First of all, this table here, you try to analyze your data, and every information in the table which you have put there and it was not given in the question gives you a chance of earning a DA, that is data analysis. Even this one was got by you, data analysis. Even this is data analysis. Then this expression here, if you write it, then you get a law. you have applied this law. We call it the equilibrium law. When we talk about law, we don't ask you to write the equilibrium law in words. We just ask you to write K C is equal to this and this. For us, we know by doing that you are applying the equilibrium law. And here you are analyzing data. You are analyzing data and you manage to get the answer. Then after that, whenever you get an answer after calculation, make sure you create meaning with it. And that one is called data interpretation. Then after that, our question required us to explain factors. By this time, I explained them verbally, but I summarized briefly. So each factor you will explain is awarded with FE. So these are factors which are being explained. Then you talk about the application. You discuss the application which result formation of sulfuric acid. This one is an application. An application. If someone went to go to fertilizers, then continues to earn applications. Then after that, we need a danger, which is a danger explained, and also a mitigation here. I talked about dangers here and how those dangers can be mitigated. So as a teacher, I'll come up with a scoring rubric, and this scoring rubric here. And in the scoring rubric, I pair laws with factors. If my marking aid has 2 laws and it has, for example, 4 factors, a student who brings all of them, I give that student a score of 3. Then I pair data interpretation together with data analysis. For example, in my work, I interpreted data once, and when I go, I look for DA or data analysis. I have 1, 2, 3, 4, and 5. So I 5. So a student who bring all of them, I'll give that student 0.3. Then I'll talk about a danger and a mitigation. You bring one danger and one mitigation. When the mitigation purely solves a danger which is well explained, then I give you a score of 2, just 1. One danger corresponding with this mitigation to give you 2. Then I'll talk about application. If you bring an application which is well explained, for example here, application I scored how many times? I scored 1, 2, 3, 4, 5. I scored 5 times. So if I give you, for example, 4 EA, then I give you a score of 0, 1. This one can be like my rubric, but not all students can be able to attain the maximum. This will make the question out of 9. But not all students can attain maximum. So I go on varying. The student now who will bring, for example, 1 law and maybe 2 FE, I give you 0.2. The student who bring 0 law and bring maybe 3 or 4 FE, that student gets 0.0. Because without a law, you don't get any mark. Even if you bring all the factors. Without data interpretation, you get 0. Without data interpretation. Without a danger, you can't get a mitigation. What are you mitigating when the danger is not well explained? Even if it's there but not well explained, you still get 0. So I want to end there for today.